Alright, so these are all reasonably similar. There's a couple of tricky little bits on some of them, but I think it was Shrish, I think, managed to do, was it 10 out of 11, maybe full marks? So they were very, very doable. Okay, so the gravitational field strength in meters per second. So if you remember, we had the equation for gravitational field strength, which was this one, okay, with our force equation being this one. So the only difference between them is having an extra mass in the force equation and have it missing in the field equation. Check your units. This should be in meters instead. So this is then 2.21 times 10 to the 7 meters. Kilograms, meters cubed, fine. Okay, so density of the planet. So things that we might be interested in. Density is equal to mass divided by volume. If it's a planet, we're assuming that it is a sphere. The volume of a sphere is, what is it? Is it 3 over 4 or no, 4 is the surface area. 3 over 4 pi r cubed. I think you have that in your data book. 4 over 3. Okay, thank you. So 4 over 3 pi r cubed. Okay, so we're probably in position to get this. So we want to get the density of the planet in those. So we change those units, so we're good. So we can substitute this back into our equation here and rearrange. So we know that the mass is going to be equal to the density times the volume. So we can substitute in the mass here for this expression. So we can say that the mass is going to be equal to, actually let's do it the other way around. 4 over 3 pi r cubed times rho. So this is our expression for the mass. So we've got a field strength, we've got a radius, we've got, okay, this is at the surface as well. So we can then start to stick some values in here. So we can say that G is going to be equal to G upon 4 over 3 pi r cubed times the density divided by r squared. And it's the density that we want to find. We can do a little bit of cancelling first off, so we can get rid of that on the bottom, and that will just leave us with r on the top. So we can say then that that will be 3g divided by 4g with pi and an r on the bottom to give us our density, and then we simply stick in some numbers. So that was 3 times 24.8 divided by 4 times 6.67 times 10 to the negative 11 times pi times our radius, which we converted in kilometers, 2.21 times 10 to the 7. And solve for density. I don't have a calculator to hand, but that is how you do that one. I've taken ages over it, but really it's just a simple substitution. Moving on to the next one. Diagram shows two planets, X and Y. So X is twice the mass of Y. The centers of the two planets are separated by a distance of 2d. Point P is midway between the planets. The mass of each planet may assume to be concentrated at its center. Okay, so that means that we can just use the ordinary Newton's equation. We want to find the magnitude of the gravitational field strength at point P. So P will be experiencing two different forces. One in that direction because of planet X, one in that direction because of planet Y. It should be smaller because while they're equidistant, the mass of Y is a little bit smaller. So we can work out the gravitational field due to each of these planets at that one particular point. So and it's field strength that we're interested in. So we can say that Gx is going to be equal to G. Oh, actually, sorry, we know X is 2m, so G times 2m divided by, it's not going to be 2d. Okay, 2d is the full distance. So we're looking for the distance from P to the center of planet X. So that is just going to be divided by d squared. Gy, g over d squared. Yep, that's fine. So we need to find the resultant of those. So really the only difference is that we've got a factor of 2 here that we don't have over there. So we can simply say that the G total is going to be equal to, and again, this is a bit like your projectile motion questions. I don't really care which direction you decide is positive, but you need to pick one. So we can say that G total should be equal to Gx plus or minus Gy. It depends on how you're doing it. Really, it should be plus Gy, where Gy is a negative. I don't really care. It's the distance, sorry, it's the difference that you're looking between them, which is just going to be equal to G over d squared. Question number next. Satellite is orbiting Earth, circular motion, height above the Earth's surface equal to the Earth's radius, acceleration of the satellite. Give your answer without units correct. 3 significant figures. So if we've got our center, we've got the Earth, we've got the satellite orbit. So if this is R, then this is 2R. Okay, so acceleration pretty much is the same as field strength. So it hasn't given us anything equal, yep. So it hasn't told us anything about time, it hasn't told us anything about velocities. So here we're just simply looking for G is equal to G divided by R squared, but in this case the R squared isn't going to be R squared, it's going to be 2R squared given the values that they've given us. So that'll be G is equal to dm 2R squared. So that should be the acceleration on the satellite at that point. Again, pretty straightforward. Question 4. Okay, so again, we've got gravitational field strengths. So we've got G is equal to, okay, so that's just with M and D. G is equal to G divided by D squared. And we want to compare that to something where we've got 2m but d of 2. Okay, so we can logic this out. Okay, so if we have decreased our denominator, well then we've increased this whole thing. Okay, so we've got an increase of a factor of 2 because of this one. We got an increase of a factor of 2 because of this one. That denominator increase is doubled because of that one. So we've got, should be equal to 8g. Okay, so that seems to make sense because we have an increase because we've doubled the mass. Your dings are suggesting that I made a mistake. D over 2 from center. Oh wait, is that field strength rather than mass, is it? Yeah, well done. Sorry, my bad. You're entirely right. The 2m doesn't matter because it's the field strength that we're looking for rather than the actual force. Yep, thanks, yeah, being completely wrong. So that 2 doesn't factor into it because we're not interested in the force on the mass. If it was like the planet was doubled, well then yeah, I'd be fine. So you're right. Should only be 4. Question number 5. Moon has that mass. Oh no, pesky kilometers. Okay, so this should be, again, fairly similar to the others. Gm divided by r squared. Three, four. So simply stick it in your calculator, crunch some numbers. Do just be aware and careful of your negative exponents. Very, very easy to leave those off. And do make sure that you're squaring the full of the denominator whenever you're doubling and halving things and adding standard form bits and pieces. Okay, in which regions can the gravitational field strength due to 2 planets be 0? We've seen very, very similar questions to this before. Maybe with the electric field stuff, there you could have positives and negatives, so these are a little bit different. So if we were to put something in position A, it would be attracted to M, it would be attracted to M, so no, they cannot cancel out. Position C will be attracted to M, it will be attracted to M, so it cannot be there, so it must only be somewhere in B, like over here, closer to the small mass than to the big mass. So maybe very trivial, but if they put that beside charge is one that can mess people up because then you got positives and negatives. Ooh. This was a nice question. It looked rather confusing when I looked at it first, but it's pretty straightforward. So these binary star systems actually happen all the time. Um, Almost all of the stars that you can see in the sky, they are binary star systems. But I'm just too far away for you to see the two different stars. So we have some common center that these things are orbiting around, but they're both sort of orbiting around each other. Okay, so I'm going to ignore this one for the time being. So the centripetal force on this one is because of the gravitational force on the other one. So both of these are going to have equal and opposite forces. So this is a little bit weird, okay? So we've got a circular motion question here with a radius, but then the actual gravitational force causing that centripetal force, or being that centripetal force, is going to be at a distance of 2r. Okay, so we want to find the velocity. So we can come up with a couple of expressions. We know that we've got our centripetal force, so we've got our mv squared divided by r, because it's velocity we're interested in, is our centripetal force, which is equal to g m squared, two identical masses in this case, divided by 2r squared. Okay, so we do have a centripetal force with only one r because they're going in a circle at that radius, but the object that's causing the force is at a distance of 2r. So then we just need to do some cancelling so we can get rid of, oh yeah, can we do that? So we can cancel one of those. That's fine. So we've got v squared is equal to g times r divided by 4r squared. So get rid of that. So it should be v is equal to so it looks confusing, but maybe not all that complicated. Okay, pesky kilometers, check out those. So it's giving us masses, so we're good to go. So the total radius is going to be equal to the radius of the Earth plus the height. So that's 646,520. So that's our actual radius. We've got the mass of the Earth. Have they told us anything else? No. Okay, so we want to find the velocity, same as before. Now we can either do it in terms of force or we can do it in terms of just an acceleration. So we could say that mv squared divided by r is going to be equal to g m divided by r squared, or we could say that v squared over r is equal to g m over r squared. Okay, so we've got a choice here whether we're looking at force or acceleration. But either way, we're going to do it the same. In fact, maybe we don't have a choice. Maybe we have to do it in terms of acceleration because we don't have the mass of the satellite. So we'll use this one. So we can get rid of that. And all we need to do then is that 6.67 times 10 to the negative 11 times 5.97 times 10 to 24 divided by 6520 times 10 to 3. I know that's horrible. Your math teacher would shout at you for that not being standard form. In fact, it's arguably not even engineering form, but it's a nice little quick and lazy shortcut of changing between units, I find. So that's equal to v squared. So multiply them out, square root it, and you should be good. Steve, yuck. Sounds like biology. Ooh, nanonewtons. What's a nanonewton? So 10 to the negative 9 newtons is a nanonewton. Okay, so using our force equation, Gm over r squared. We're assuming there, so we're assuming that both Steve and Claire are spherical. Okay. That's a big distance in between them. It can't be that good a date. Yeah, so simply stick them in. You're probably going to get something like 10 to the negative 9 or 10 to the negative 10, and then simply convert that to your nanometers. Ooh, okay, so we've got at an altitude of 1 Earth radius, the altitude of the satellite surface triples. Ugh, yuck. Okay, so we're starting off with our satellite at height r. Okay, so the actual distance for our satellite is going to be 2r. Then they said that the altitude of the satellite triples. So not the radius, but the altitude. So this value. So it goes 1, 2, 3 to this new altitude. Okay, so at this position, we had an actual circular radius of 2r. At this position, should be a circular radius of 4r. Okay, so that's an interesting tripling. And we want the factor of the speed change. So we've got v squared over r is equal to g divided by r squared, same as we have before. So we know that v is going to be equal to gm, or that just v proportional to 1 over r. We don't have any mass changes, so we don't really care about those. So we have effectively doubled our radius from 2r to 4r, even though they were talking about triplings and other things. That's not actually what's happened. So if we've doubled our radius, well then that means that what v should decrease by a factor of 2. Is that correct? Or have I been very lazy and taken a shortcut? I think that's correct. No, wait, hang on, what am I doing? No, I'm stupid. So v is not proportional to 1 over r. It's 1 over root r. So what are we doing then? Well, let's not do it that then. There we go. That's easy. So we've r doubles, so v squared then should go up by a factor of, no, hang on. I don't do these often enough to get it right. So v increases by root 2, is that correct? Yeah, okay, thank you. Yep, so sub it in, rearrange, and try not to get confused by ratios. I did take a shortcut there. If you actually just equate them and put in some numbers, it's much easier to get your answer out. How am I doing for time? Not too bad. Ooh, gigameters. So we've got our two masses, 1.6 times 10 to the 11 meters separating these two. Both 10 to the 24s, so we have 9 and 5. The third mass is placed between the two masses so that it remains stationary. If it remains stationary, that means there is no acceleration, so there is a zero resultant force. So it means that the gravitational fields are going to cancel out. This might be a simultaneous equation, perhaps. We want to find the distance from here that it's placed. Okay, so let's put in our distance. Let's call this distance d. This other distance then is going to be equal to 1.6 times 10 to the 11 minus d. And we can equate our two field strengths. Is equal to g other n divided by 1.6. So we can get rid of g's, we don't care. We put in our numbers, 9 times 10 to the 24 divided by d squared is equal to 5 times 10 to the 24 divided by 1.6 times 10 to the 11 minus d squared. We can get rid of our factors of 24. We don't particularly care. Let's bring things up to the top line. So we've got 9 1.6 times 10 to the 11 minus d all squared. Yep. Is equal to 5 d squared. Nearly there. What's 1.6 squared? So that's 1 minus. Okay, so I think that's correct. Might not be though. Let's take our d squared over to the other side. So we're left with 4d squared plus 3.2 times 10 to the 11 d minus 2.56 times 10 to the 22 is equal to 0. And then you can do your quadratic formula. You're not going to be asked to use quadratic formula in your actual IB exam, but that absolutely is one way to be able to try and solve these and take it through. So go through, find your roots. One will be negative, don't use the negative one, and then your other one is good. So those are your 11. A couple of those were a bit tricky. This one was probably a little bit tricky. That one maybe a little bit tricky with their sort of where they've talked about their doubles and triples and things. This is really easy. You should have definitely gotten that one. All these velocity of orbit circular motion questions should have been fairly straightforward as well had you done the pre-reading and not just flicked through and pretended that you'd read it. So well done to those of you who did well. Those of you who were getting like less than half on these, I would expect that probably you're doing a little bit better than that. Any questions, any observations, anything to mention with these?